All right, hello, greetings, welcome. I wanted to take a look at exercise 2.4, which you're asked to solve for your homework this year. So in your transport phenomenon course, fluid mechanics, you likely solved many problems that required you to read values of friction constants from a Moody chart or to use analytic expressions for the friction factor over a limited range. Recently, these authors published an article in AICHE Journal entitled A New Six-Parameter Model to Estimate the Friction Factor. In that work, the authors proposed a new analytic expression containing 6 parameters that is capable of estimating the friction factor for flow in pipes at all conditions. So for all Reynolds numbers and relative roughnesses, the proposed expression takes this form. Okay, so F is my friction factor. RE is my Reynolds number, which is a variable, so it's going to be a precondition. It's going to be something someone's going to have to specify. And my relative roughness, which is also going to be an input, something that someone's going to specify. So my Reynolds number is dimensionless, my relative roughness is dimensionless. We also have what appear to be 4 other variables, but they're really just parameters. We have lambda 1, lambda 2, tau 1, and tau 2. Okay. But lambda 1 and tau 1, they're just constants. And then lambda 2 and tau 2 are just functions of my relative roughness. So I have this expression here where F is my friction factor that I want to calculate. It has 2 variables, my Reynolds number and relative roughness. So they're going to be preconditions. They're going to be variables that the user is going to have to specify. And once those are specified, I can return F, my friction constant. Okay, and so you can read the rest, but let's set up and write a script that uses this equation, okay, to calculate my friction factor. And then we can answer the questions, right? And the first one is just looking at a specific case to test that our code is working correctly. Okay, so I'm going to start. I have a new session open. I'll create a new script. Okay. And let's start with our preconditions, our postconditions, and we can come up with a little description of what our program does. So this is going to be a script to compute the friction factor for a given Reynolds and relative roughness. Okay. All right, and so we're going to have preconditions, and our preconditions are going to be, okay, I'm going to use a lowercase number, my Reynolds number, and I'll call it ED, which is going to be my relative roughness. Okay. Relative roughness is nice because then it's dimensionless. I'm going to have a post condition. Okay. And my post condition will be F, which will be my friction factor, okay, which is also dimensionless. And then let's do it. So if I want to go about calculating my friction factor, okay, as we saw in the equation, right, it's a function of my Reynolds number and my relative roughness. I need lambda 1, lambda 2, tau 1, and tau 2. So I'm going to actually scroll ahead, and I'm going to start with the calculation of lambda 1, tau 1, lambda 2, and tau 2 that I can use back in my equation. Okay. So in terms of lambda, right, I could call it lambda, I could call it L1 or L2. It's really up to you. Okay, and if you're not sure, you can add a comment. So let me call this, say, lambda 1 and tau 1, right? And so lambda 1 is 0.02. Okay, tau 1, okay, I'm just going to use T1. Okay, remember, there's no Greek characters. So tau 1 is 3000. Okay, now I can calculate lambda 2 and tau 2. So as I calculate lambda 2, right, I'm going to take this in pieces, and you can even break it up in multiple steps if you wanted. Okay, but I'm going to go to lambda 2. Okay, and if I'm going to be correct in my Greek, right, that's a lowercase lambda. Okay, so as I calculate lambda 2, okay, I'm going to take this in steps. Okay, so first, if I look at, let me see, how do I want to break this up? Let me start by typing up the denominator. So it's -2 log base 10 of my relative roughness divided by 3.7065, right? This is my relative roughness, which is a precondition which we're taking to be a variable, right? Because when we look at the problems, right, we're specifying relative roughness and not, say, roughness or the diameter of a pipe, right? Usually it'd be the diameter of your pipe, and the roughness is this intrinsic property of that pipe. But anyways, so let's do the bottom first. Okay, so I'm going to have lambda 2. Okay, and just from a typing standpoint, I'm going to start by typing in the denominator. So it's negative 2. Okay, log 10 is log 10, and the argument of log 10 is my relative roughness divided by 3.7065. Okay, so it's going to be ED, right, my precondition, my relative roughness, divided by 3.7065. Okay, cool. And so that's this term. Okay, now this term in parentheses is 1 divided by that. Okay, so it's 1 divided by this. Okay, and just to be certain, I'm going to put that denominator in parentheses. Okay, well, it's 1 divided by that, and that all squared. So now I'm going to add parentheses around everything so that I can square it. Okay, and we haven't discussed element-wise operators, so it's just a power 2. Okay, so now I have this squared, and I want lambda 1 minus that. Okay, so I want lambda 1 minus that term. And then the last piece is I want the absolute value. And so MATLAB has a built-in function abs. I can just type abs, right? The absolute value is the square root of the argument squared, right? And so if you really wanted to, you could do that. And so I would, instead of having abs, right, I would take that term in parentheses and I'd square it and then take the square root of that. Okay, but we can do absolute value, and that works. So there's lambda 2. Okay, and the next tau 2. Okay. So let me just say, so our first 2 parameters are constant. Our second 2 parameters are functions of the relative roughness. Okay, so for tau 2 then, I'm going to type, I'll take it one term at a time, since this, sorry, I keep flipping the wrong screen. This one's a little more straightforward. So 0.775, 0.5 divided by, okay, and now it's my relative roughness squared. So it's ED squared in terms of the notation. And order of operations, right, it should square this first, but I'm just going to add parentheses in terms of being anal. And oftentimes I even add parentheses around my exponent, which would be, say, doing that. Completely unnecessary, but it's something I'm also just in the habit of doing often. Okay, so when in doubt, right, you can add parentheses, they don't hurt. Okay, it's going to be that minus 10.984 divided by ED. Okay, and then that is plus. Just like if I want to put the second term in parentheses, I could. But it's just plus 7953.8. Okay, and yeah, so if I want to put this in parentheses, I could. If I want to put parentheses around that, I could. Right? When in doubt, add parentheses. Right? Better to be safe than sorry. Which is, kind of takes us to this first task, is when I'm writing a code. right? It's useful to try and evaluate it under set conditions so that I can test to make sure it works before I extend it to other systems, right? To make sure there isn't a small issue that I've made, such as missed parentheses or anything of that nature. Okay, so now I'm going to plug it into my larger expression, and we could break it up. Let's start typing it and see what it looks like. Okay, now, so computing f. So f, okay, f, which is, what I have listed as my post condition, is 64 divided by my Reynolds number, right, which I say is RE. And that's just a habit of mine, is when I have a scalar variable, I tend to use lowercase. I tend to reserve uppercase for once we have vectors, which will come later. Okay, so my second term is lambda 1 divided by, okay, and I'm going to put the denominator in parentheses. Okay, and as a comment here, one of the things that's changed in versions of MATLAB, so on my desktop here it's 2022a, is that it tries to auto end my parentheses to try and prevent errors such as not closing up your parentheses. Okay. So 1 plus, okay, then e is exponential, and then I'm going to have tau 1 minus Reynolds, okay, and that's the numerator and that argument within my exponential, divided by 100. Okay, so I have a set of parentheses, right, for the argument in my exponential, and within that argument I have a fraction, so numerator is tau 1 minus Reynolds in parentheses divided by 100. So that's term 1. Then term 2 is going to be similar. So let's do it. So term 2 is going to be lambda 2, okay, divided by, I'm going to put a bunch of extra spaces in there, 1 plus exponential. So within the exponential, let's do it just as we have it written. So in the numerator, it's going to be tau 2 minus Reynolds divided by 600. And then in my order of operations, it should be okay, because it'll take this, divide by 600, and then multiply by my relative roughness. Okay, if you wanted extra parentheses to break it up, you could. All right, and that's it. So I'm not going to suppress the output for the second one. Okay, let me call this friction factor.m, and I'm going to save it. Okay, but I'm not going to suppress the output for this last line, so it displays that final result of the calculation when I run it. And so then looking at the first case says test your code for the case of a Reynolds of this. Okay, so my precondition Reynolds is 1e to the 5, and relative roughness of 1 over 30. So that's ED is what I said, right? RE and ED. ED is 1 over 30. And so when I do that, and then I call friction factor, okay, and so I typed that pretty fast, right? All I did is I tabbed it, okay, and it auto-completed. Type friction factor. Oh no, I have an error. Okay, let's go back and troubleshoot. Unrecognized function or variable lambda 1, and the error first appears in line 16. So the issue is here I call that L1 and T1. Okay. So if I want to be consistent here, I'm going to call it lambda 1 and then tau 1. Okay. Okay. I'll save it. Okay, and I'll try again. Okay. And now I have error using real. Nope, sorry. In line 21. Not enough. Oh, so this is, my guess is it auto-completed on me. All right, that was supposed to be RE, Reynolds number. Okay, so I try again. I get 0.601, all right, which is exactly the right answer. Okay, good. So sorry I didn't get it perfect the first time, but it shows, me genuinely working through it and making two mistakes. So the first error I made when I first wrote it is I thought to try and shorten up the notation I was using, and I used L1 and T1 for lambda 1 and tau 1, but then only in my head to type it out here. And so the error that I received told me that there was an unknown variable lambda 1 because I had defined L1 previously, and so it tells you it's missing, and it tells you, right, gives you the line of where that error is first accounted. So even though I misdefined it on line 11, right, the error appears on line 16, which is where it first tried to use that variable. Right? Technically, when I had L1 here, I didn't do anything wrong. That was a valid mathematical expression. Okay? But the error appeared here because that was the first time that I actually tried to use that variable. Right? And so that's where the error occurred, and that's what you're given notice of. Okay? And this is a smaller, simplistic example, but that's also part of the motivation of why we try and advocate incremental development. Is you want to test your code before you get too far along, so that when errors like this appear, you can try and catch them as early as possible. Right? And so it wouldn't have been a bad idea of after lines 16 and 18 to run my code to see if I had any errors before I got to line 21. Right? But really, you don't have very many lines here, so it wouldn't have made a huge difference. Okay. Then the second error that appeared is I had this error using real. And what that is I swear this didn't used to happen on earlier versions of MATLAB, but it seems like this version of MATLAB goes overkill in terms of autocomplete. And so the autocomplete was, as soon as I started typing RE, it was trying to fill it in. Right here, the first suggestion is RE, which I have defined now in my workspace, but it wasn't while I was writing the code, and I think that was the problem that tripped it up. Okay, but again, it gives you the exact line where it happened, and then looking back, I had no variable real, right? That's something that they must have added. Okay, so yeah, so that's now working code for this problem. And if you wanted to test it out, right, it asks, does F increase or decrease when Reynolds increases? Okay. Well, in this first case, we have a Reynolds of 1e to the negative 5, and I get a friction factor of 0.601. Okay. If I were to change Reynolds to 1e to the negative 6, okay, and then run again, okay, it's 0.50598, so it's decreased slightly. Okay. And what I'm using here to recall commands is just on the keyboard, just the up button. Okay, it'll allow you to go back through the history. Okay, and so if I make that 1e to the negative 8, okay, I run friction factor, it's decreased slightly. It's hard to see at this point. So maybe if I go in the opposite direction, 1e to the 3, so if I decrease Reynolds and run it, right, now we've gone in the opposite direction where it's increased. And so that's part of the fun of playing with MATLAB is we can set up these models, and then we can turn knobs, right? And we can, kind of do a virtual experiment, if you will, a numerical experiment in terms of trying to come up with, understand, what's happening physically, right? So as the Reynolds number increases, right, the friction factor decreases. And so if everything else were constant and I were to increase the velocity of my fluid, well, then the friction goes down. And same thing with roughness, right? We'd expect as roughness increases, friction increases. So if I go back to Reynolds of 1e to the negative 5, and ED was originally 1 divided by 30, but if I make it 1 divided by 10, so actually let me make it 1 divided by 30. So let me go, so originally it was 1 divided by 30, right? And so you get a friction of 0.06. If I make it 110, so increasing the relative roughness, okay, so effectively decreasing the diameter, all right, then it goes up, all right? So as the relative roughness increases, the friction factor increases, and you could put more examples in there to test it. Okay. Last comment, right, is again here this is yellow, all right? This is just as we get going. in general, we're going to end up writing functions where we suppress our output, and so we use the function as controlling, um, returns of information. Okay, but all is good. Let me know if you have any questions. I hope that helps.